Welcome to this video here. We're discussing how we might interpret the sum of binomials, and in particular, what we are trying to attempt here is to prove that this formula exists in fact. So we have this formula. So we have essentially the sum of two binomial distributions, x being binomial of np and y being binomial of mp. Then we can add up the two independent binomial variables and get another binomial distributed random variable, which is binomial of n plus mp. Okay, so we explained in this video over here. Of course, this here is the main theorem that we make use of, or this is the main rule that we make use of. It comes from the expansion of the identity over here, 1 plus x to the power r plus s. So if you expand that using the binomial theorem, what you then get is this identity here, and this is our main identity that essentially proves that the sum of binomials is again a binomial. I should say sum of binomial distributions really. Okay, so let's move on now, and moving on, let's look at this overview video that has been curated over here. Welcome to this video here. So we're considering how we might model the sum of binomials. So if x is binomial distributed and y is binomial distributed, n and p, and they are independent with the same probability p, then x plus y is again a binomial variable. Its distribution is z equals x plus y, and it's a binomial of m plus n uh, coefficients. So that's simply, in fact, it's just the convolution sum of binomial np and binomial mp, and that when you use the binomial formula, it comes out to n plus m choose k, p to the k 1 minus p to the power n plus m minus k. A binomial distribution random variable x binomial np can be considered as the sum of n Bernoulli distributed random variables. So of course, the sum of two binomial distributed random variables is equivalent to the sum of n plus m Bernoulli distributed random variables. And of course, we prove this using the addition rule. However, if x and y do not have the same probability p, then the variance of the sum will be smaller than the variance of a binomial variable distributed as binomial of n plus m choose p. The Poisson binomial distribution. Binomial distribution is a special case of the Poisson binomial distribution, which is the distribution of a sum of n independent non-identical Bernoulli trials, B of pi. Alright, so there we've tried to explain how you can add up two binomial variables and get a third binomial variable, that is x plus y. So here we have this primary equation which allows us to understand the sum of binomial distributions. So of course, the main theorem here is that if you have a convolution sum of coefficients r choose k and s choose n minus k, for some fixed n, and you run the parameter k between 0 and n. So what that really looks like is you have these coefficients of r and s, where the indices for r go from 0 to n, and for s go from n to 0. And this actually sums out actually to be just the coefficient r plus s evaluated at n. So to prove that, it really suffices to just expand the coefficient, the product 1 plus x to the power r plus s. And if you expand the left hand side, what you get is r plus s choose k times x to the n for n equals 0 to r plus s. And if you expand the right hand side, what you get is x to the n sorry, you get the sum of x to the n from 0 to r plus s, and you get the sum of and then that is multiplied individually by the sum of r choose k, s choose j for k and j summing to n always for all the possibilities of k and j. So that's essentially just this or the right hand side. And what you realize, if you just compare the nth coefficient, or rather if you can compare the uh, let's say tth coefficient, then what you get is the left hand side would just be r plus s, uh, or rather, yeah, it suffices really, in fact, just to compare the nth coefficient. So r plus s choose n times x to the x to the power n, and here what you're going to get is this sum over here. So what you end up with essentially is that this simple thing you end up with, which is that um, you just simply eliminate the coefficient x to the n, and what you get is let me just hang on there a second. In fact, and here you get you just have to eliminate this sum here. All right. So you get the sum of r choose k, s choose j, as k and j run between 0 and n. You have that is equal to r plus s choose k, which is exactly this formula. And this allows you to prove essentially here this sum, because the p's will just cancel out to p to the k, whereas the 1 minus p's will cancel out to n plus m minus k. The i's will cancel out in the exponents. So what you just have is the sum of the convolution sum of n choose I and m choose k minus I as I goes from 0 to k. And using the identity here, this is actually called Vander Monde identity. This is Vander Monde identity. So using Vander Monde identity, you get that r plus s choose k equals the convolution sum of r choose k and s choose j for all possibilities of k and j between 0 and n, all integer possibilities. So please reach out to me if you have any questions, and send them to me directly at stashglc@gmail.com. Thank you.